Hi everyone. This is the last video for our lecture for chapter 19, and we're going to talk about the internal energy and molar heat capacity of gases. So let me go ahead and bring up the notepad here. So first of all, we need to recall we've talked about the internal energy of a gas before when we talked about the first law of thermodynamics. And the internal energy is the energy stored in the gas. Now, in the last lecture, we learned that internal energy is due to kinetic energy due to the motion of the molecules in the gas. So if we want to talk about the total internal energy of the gas, it's going to be the number of molecules times the average kinetic energy of each molecule. For a monatomic ideal gas with a single atom, the number of atoms or molecules is just the number of moles times Avogadro's number. But we found that the average kinetic energy is 3/2 kT. K again is the Boltzmann constant. Or you could write this internal energy as 3/2 times number of moles times R, 8.31 joules per mole Kelvin ideal gas constant, times the temperature of the gas. So for an ideal gas, the internal energy is directly related to the temperature. Right? The greater the temperature, the greater the internal energy, greater average kinetic energy. So one thing we can figure out now is what's called a molar specific heat, which means the heat capacity per mole instead of per mass. Right? So what we mean then is that the heat absorbed or lost by the gas is proportional to the change in temperature by the number of moles times this molar specific heat. Now in this case, we're talking about a constant volume process. We might get different specific heats depending on how the gas changes. In this case, we're going to talk first of all, what if we keep the volume constant? But this is our definition of any kind of molar specific heat, NC delta T. So from the first law of thermodynamics, we remember that the change in internal energy of the gas is Q, right? The heat minus the work done by the gas. So for a constant volume, we write Q as NCV delta T. And we remember if the volume's constant, there's no work done by the gas. So W is equal to 0. Then we can solve for CV, and again, recalling that change in internal energy would be 3/2 NR delta T. We can get this. The N delta T's cancel, and we find that CV is 3/2 R. So the molar specific heat is 3/2 R for a constant volume process, or about 12.5 joules per mole Kelvin. So what this means is it takes 12.5 joules to increase the temperature of an ideal monatomic gas at constant volume by 1 Kelvin for 1 mole of the gas. Right? We could also talk about the molar specific heat at a constant pressure. Now in this case, there's going to be work done by the gas. If it expands, the volume is not held constant. We're just holding the pressure constant. But we recall from the definition of work, in that case, it's just pressure times change in volume. But the ideal gas law is nRT, which in this case would be nR delta T. So our work is just nR delta T in this case. Again, going back to our first law of thermodynamics, change in internal energy is Q minus W. And what we end up getting is our delta E internal is 3/2 NR delta T. That's equal to Q, which we're now writing as NCP delta T, because we're talking about a constant pressure molar specific heat process, minus our NR delta T work. So kind of solving, we find that the CP is 3/2 R plus R. Now 3/2 R was CV, so we could write this as CP equals CV plus R, or it's equal to 5/2 R. So the specific heat, molar specific heat at constant pressure is bigger than at constant volume. And this makes some sense because it you got to add more heat if you're expanding the gas and increasing the temperature, right? So the specific heat's going to be bigger in that particular case. As far as the problems go, you may use either one of these depending on whether it's a constant volume or a constant pressure process. So just to kind of summarize, I've written that the amount of heat taken for constant volume is 3/2 nR delta T. For constant pressure, it's 5/2 nR delta T. And one last thing about this, when people actually went and done the experiments for different gases, for constant volume processes, the 3/2 R only works at low enough temperatures for diatomic gases. So let's say you had a hydrogen gas or a nitrogen. Normally the gas comes as a diatomic molecule, two hydrogens stuck together. And so they can move or translate, but they can also rotate and vibrate. Now, if you're at low enough temperature, surprisingly, you get the right answer that we just derived, 3/2 R. But if you get to a certain high enough temperature, it kind of jumps up to 5/2 R. And then if you get to even higher temperatures, it goes to 7/2 R. And this was really a big puzzle around 1900 or so, because why? First of all, why is it bigger than what you'd expect? And also, why does it have these jumps? And the answer actually, surprisingly enough, turns out to be due to quantum mechanics. This was one of the first indications that you've got to use quantum physics to explain some of the properties of molecules and atoms, as it turns out. It just turns out you cannot explain it in terms of a classical physics model. But it does turn out, in a lot of cases, you can use what's called the equipartition theorem. For each degree of freedom, you get 1/2 R contribution to the specific heat at constant volume. So what do I mean by that? So if you're translating, right, you can move this way, or that way. That's 3 degrees of freedom. And that's why you get a 3/2 R if you're just translating. Now, if you can rotate, you've actually got 2 more degrees of freedom. And that jumps it up to 5/2 R. If you can vibrate, you've actually got a couple more degrees of freedom, and that gets you up to 7/2 R. Okay, so that was actually expected. What wasn't expected was these jumps. Now, to explain real quickly why those jumps occur, it turns out that any quantum mechanical atomic or molecular system has energy levels. So if you don't have enough energy, all you can do is translate. You got to get to a high enough temperature, a high enough energy to open up the rotational energy levels, and even higher to open up the vibrational energy levels. So again, this was just a curious thing that I wanted to mention about the specific heats. Surprisingly, to some people, when I mentioned this to them, they don't realize that quantum physics actually, first of all, came from looking at thermodynamics. Now, at this point, I'm going to end the class. We can do a lot more with thermodynamics. You can talk about what happens in adiabatic processes, free expansions, and you can look at cycles and PV diagrams that describe realistic type of engines. Right? Studying engines would commence by looking at what happens in those PV diagrams. In chapter 20, they talk about entropy, which is always really interesting to people. Unfortunately, I don't have enough time to really get much into detail. But if people are interested in that, if you have a particular interest, always you can send me a question or talk to me at some point. Hopefully, we will actually be back in the classroom, in the office, and you can come and just talk to me about this stuff if you have questions. But this should cover enough for the homework for chapter 19. Again, there is no lab for the final week of classes. There's a makeup lab. For my classes, I don't know how it works for Dr. Yang's classes, but finish up the chapter 18-19 reading quiz and a homework assignment, and you should be done with the class. So from there, I'll say goodbye. To those of you I'll see in the summer, I'll look forward to seeing you again here in a couple of weeks.